Welcome back to the channel. It's the Earth Science Classroom. This video is on the Earth's interior, and we're going to look at and focus on convection currents that occur in the asthenosphere, that weak layer of the upper mantle. We're going to look at how these form and what happens to the above layer, the lithosphere, when these convection currents are moving. This is the Earth Science Classroom. Before talking about convection currents in the asthenosphere, we first have to look at convection currents themselves and what they are. So convection is a type of thermodynamics, which is heat movement. Now, convection is looking at from hot to cold heat sources. Now, before that, we're looking at how atoms and molecules in different materials act when they absorb the energy, in this case radiation from the sun. What happens to them when they absorb that energy? So first they're going to absorb the energy, and there'll be a given amount of movement or energy within that atom. If you add more radiation, more energy into that atom through absorption, then there'll be more movement. So when you increase the energy within a material and you add in that thermal energy, that heat, what's going to do is it's going to create a different environment for those atoms, because the atoms are going to move more because they're more energized, because they've absorbed more heat and more energy, and therefore the area in which these air molecules are occupying will increase. So in this diagram I have 9 atoms basically. On the left box it's less energy, smaller box, still the 9 atoms, but in a much more higher density environment. There's less space within the atoms within the area. When you add the heat and it's absorbed, then these atoms start to move more, and they naturally space out and enlarge and increase the volume of the area that they are in. Therefore, the density is going to decrease, and there'll be more space in between the atoms, just because we've added energy and they're more energized. So the rule of thumb is when you increase the energy, you increase the temperature, you increase the movement, and then if you increase the movement, you increase the volume of the area the atoms occupy, and therefore you're going to decrease the density, because you haven't increased or decreased the amount of molecules, you just increase the size or the area or the volume in which they occupy. So density will go down or decrease. Also on the flip side, on the opposite, if you take away that heat energy and you decrease the energy in these absorbed atoms, then you're going to decrease the temperature, decrease the movement, and then decrease the volume, so it will shrink and occupy less space, and therefore that same amount of atoms will occupy a more densely populated area. So it becomes higher density when you decrease the volume, because density is mass over volume. Now here we have thermodynamics in action, whereby I have this hot plate creating the heat energy, the thermal energy, and it's being transferred into this Pyrex glass, which is sitting on top of the hot plate and transferring the heat through conduction, through touch. Then we have the bottom of this Pyrex being heated, and at the top I have a plastic bag filled with ice, which gives us that hot and cold surfaces that are separated by this liquid medium. And I've added some rheoscopic fluid and some food dye. In this case, I started with orange, now we have a little bit of green, and this food dye plus the rheoscopic fluid is allowing us to visualize and see and observe the convection currents in action. Now I'm going to add in a different food dye, and you'll see how this is being moved inside this Pyrex glass with the hot water, and where the water is rising because of the added energy and the volume, it becomes less dense, and it's going to rise relative to the surrounding temperature and density of the water. And there's a section where the water is descending and sinking because it is slightly colder, slightly more dense, and therefore it's going to sink. And you have this circulation and this current form between the hot bottom area of the water and the colder top section by the ice. So you have this flow of hot, rising water because of the density and the temperature, and it hits the ice, cools down, gets away or further away from the hot plate, going to cool down and become more dense and sink back down. And you have this beautiful flow and mixture of rising material and sinking material, creating this amazing convection current within this water. I've just shown what happens when you add convection into liquid. A similar pattern, a similar effect happens within our Earth's interior, within the Asthenosphere, which is the upper mantle. And this is a solid and semi-solid layer, which is roughly around 600 kilometers thick, about 400 miles thick. And this sits right below the MOHO, which separates the asthenosphere, or the upper mantle, to the lithosphere and crust. The lithosphere is solid and brittle and contains the crust, both the oceanic and continental. And then underneath the asthenosphere, the layer below, which is the lower mantle, is called the mesosphere. And this is generally very dense and solid rock. Now, the asthenosphere is called astheno because it means weak in Greek. Now, the weak comes from the partial melting that occurs when the temperature goes above the pressure and allows the material to melt. Now, we know that a material going from solid to liquid generally needs more area to occupy when it melts. That's also why the inner core, even though it's so hot at around 6,000 degrees Celsius, it's still solid because of the pressure that keeps it in that solid phase. If you were to loosen the pressure, the inner core would go into a liquid state, like the outer core. But the asthenosphere is partially melted, and this creates convection between the warmer, hotter mesosphere at the bottom and the cooler lithosphere, or the base of the lithosphere, around 50 to 100 kilometers in range. And this is between 1,000 to 1,200 degrees Celsius, and the bottom, where the mesosphere is around 2,000 degrees Celsius. There's a difference there between hot and cold, and you get this convection moving rocky material, partially melted rock, up towards the lithosphere, and then it's going to sink back down again towards the lower mantle. This takes a long time, and this is billions of tons of rock partially melted, moving slowly towards the surface and back down towards the mesosphere. This is convection, and this happens in the asthenosphere every second because the heat from the Earth's core is consistent, therefore driving this flow of heat, this convection current mechanism within this layer of the upper mantle. And this forms the basis for our understanding of plate tectonics. Because the lithosphere is solid and brittle, it is broken into large pieces or fragments called tectonic plates, and these are broken by the convection currents and are moved concurrently by the convection currents, thus creating all of the crustal deformation on the lithosphere and the surface, creating our amazing volcanoes, our ring of fire, our subduction zones, our mid-ocean ridges and divergent plate boundaries, and all these amazing forces at work, also creating our lovely earthquakes and tsunamis. This is the Earth Science Classroom. Thanks for watching the video. If you liked it, please subscribe, like, and share. And if you want more content and videos on Earth Science, please check out my channel.